My name is Pranav, and today I'll be presenting the paper Driller, Augmenting Fuzzing Through Selective Symbolic Execution, which was published at the NDSS Security Conference in 2016 by researchers from UC Santa Barbara. This paper is about automated vulnerability discovery, which means using software tools to automatically find bugs in programs, especially bugs that attackers could exploit. The main idea behind Driller is that two major vulnerability discovery techniques, fuzzing and symbolic execution, each have strengths and weaknesses. The authors propose combining them in a smart way so that each technique compensates for the other's weaknesses. By the end of this presentation, I want you to understand why vulnerability discovery is hard, how fuzzing and symbolic execution work, what Driller does differently, and why combining these techniques works better than using either alone. So, quick question to think about. Have you ever wondered how security researchers find bugs in huge programs without manually reading millions of lines of code? Automated analysis tools like Driller are one of the key answers to that problem. So why do we care? So the authors start by pointing out that memory corruption vulnerabilities are still extremely common in software. These types of vulnerabilities allow attackers to crash programs, execute malicious code, steal sensitive data, or take control of systems. Even with modern protections, memory bugs still account for a large percentage of security vulnerabilities discovered every year. And as software becomes more complex, especially with things like Internet of Things devices, the number of systems that could contain vulnerabilities keeps growing. Another problem is scale. There's too much software for humans to analyze manually. So security researchers rely heavily on automated tools that can test programs and discover bugs automatically. One interesting real-world example mentioned in the paper is the DARPA Cyber Grand Challenge. This was a government competition where teams built systems that could automatically find vulnerabilities, automatically exploit them, and automatically patch them. So systems like Driller are directly related to this goal of automated cyber defense. So if you had to test a program with millions of possible inputs, how would you even start looking for vulnerabilities? This leads us into the techniques researchers currently use. There are two major techniques used in automated vulnerability discovery. Fuzzing is one, and symbolic execution is the other. Each one approaches the problem very differently. First, fuzzing. Fuzzing works by generating lots of random inputs and feeding them into a program. The goal is simple. If the program crashes, we might have found a vulnerability. Modern fuzzers mutate inputs in intelligent ways and track code coverage, meaning they try to discover new program paths. The advantages of fuzzing are it is very fast, it runs programs natively, it can explore a lot of program paths quickly. But fuzzing has a big limitation. It struggles when a program requires very specific input values. For example, imagine a program that checks if input equals a specific magic number. A fuzzer randomly mutating input might take an extremely long time to guess that exact value. Now let's look at symbolic execution. Symbolic execution treats inputs as symbolic variables instead of concrete values. Instead of trying random inputs, it mathematically analyzes the program and determines what inputs are required to reach certain paths. This allows symbolic execution to solve complex conditions, but it also has a major drawback. It suffers from something called path explosion problem. That means the number of possible execution paths grow exponentially. making analysis extremely slow. So now we have two tools, one that is fast but not precise, and one that is precise but slow. And that leads to the core idea of Driller. But first, let's look a little more closely at their limitations. Let's start by understanding fuzzing in a bit more detail. In fuzzing, the system takes an input and repeatedly mutates it, changing bytes, inserting data, or flipping bits, and runs the program with those mutated inputs. If a mutation leads to a crash, the system saves that input as a potential vulnerability trigger. The reason fuzzing works so well is that it executes the program very quickly, allowing millions of test cases to run. But fuzzers rely heavily on random mutation. And this becomes a problem when programs require very specific values. For example, imagine a program with a check like the one to the right. X equals some number, and if that if that condition is hit, then vulnerable will be executed. The probability of randomly guessing that exact 32-bit value is extremely small. The paper actually explains that the chance could be something like 1 in 2 to the power of 32. So even if a fuzzer runs millions of inputs, it might still never find the correct value. So let me ask a quick question. If a program requires an exact password or checksum before executing deeper code, do you think fuzzing alone could easily reach that deeper code? Usually not. That's where symbolic execution can help. Symbolic execution approaches the problem differently. Instead of guessing input values randomly, it analyzes the problem's logic. Inputs are treated as symbolic variables, and the system records constraints as it explores program paths. For example, if the program contains a condition like the one on the left, x equals some hex value, the symbolic execution engine can solve that constraint and determine that x must be equal to the value shown. This allows it to reach the program paths that fuzzing would struggle to discover. But symbolic execution has its own major problem. It quickly encounters path explosion. Every conditional branch creates multiple possible execution paths. For large programs, the number of possible paths grows exponentially. For example, if a program has many nested conditions, the number of paths can become enormous. The paper gives an example where exploring all paths could require analyzing hundreds of millions of execution paths. So symbolic execution becomes extremely slow and impractical for large applications. So now we have the core problem. Fuzzing is fast but can miss deeper bugs, and symbolic execution is precise but doesn't scale very well. So the natural question is, what if we would combine them? That's exactly what Driller does. The key insight of Driller is that programs can be thought of as being divided into compartments. These compartments are separated by checks on specific inputs. Inside each compartment, the program processes general input and has many possible behaviors. Fuzzing is actually very good at exploring these compartments, but moving between compartments often requires satisfying complex checks. This is where symbolic execution is useful. So Driller combines both techniques in a hybrid workflow. Here's the basic process. 1. Start fuzzing the program. Next, fuzzing explores many paths quickly. 3. When the fuzzer gets stuck, Driller invokes symbolic execution. 4. Symbolic execution solves the constraint blocking progress. And then the 5th step, the new input is sent back to the fuzzer. This process repeats, allowing the system to gradually explore deeper parts of the program. Think of it like this. Fuzzing digs horizontally across program paths. Symbolic execution acts like a drill that breaks through barriers. This is actually where the name driller comes from. So a quick question. Why do you think the system only uses symbolic execution when the fuzzer gets stuck? Because symbolic execution is expensive, so we want to use it only when necessary. This slide summarizes the workflow. The system starts with fuzzing. When fuzzing stops finding new paths, the system switches to concolic execution, which is a combination of concrete and symbolic execution. Concolic execution analyzes the path taken by an input and identifies conditions that prevented exploration of other paths. It then generates new inputs that satisfy those conditions. Those inputs are passed back to the fuzzer. Then fuzzing continues exploring new areas of the program. This loop continues until a vulnerability is discovered or analysis stops. So instead of exploring everything symbolically, Driller uses symbolic reasoning only where it's needed. One important optimization in Driller is something called pre-constraining. This helps avoid the path explosion problem in symbolic execution. When Driller runs symbolic execution, it constrains the symbolic input so that it initially follows the same execution path discovered by fuzzing. This means symbolic execution doesn't explore every possible branch. Instead, it only focuses on the path already discovered. Then when it encounters a branch where fuzzing failed to explore the alternative path, it removes the constraint and solves for the new condition. This allows it to generate a new input that leads to a previously unexplored path. This optimization is important because it keeps symbolic execution manageable. Without it, symbolic execution could quickly become overwhelmed by too many paths. To evaluate Driller, the authors tested it on 126 binaries from the DARPA Cyber Grand Challenge dataset. These programs were designed to contain vulnerabilities and challenge automated analysis tools. Each binary was analyzed for 24 hours, which matches the time limits used in the competition. The researchers compared 3 approaches: pure fuzzing, pure symbolic execution, and Driller's hybrid approach. This allowed them to see how well Driller performed compared to existing techniques. The results are really interesting. Out of the 126 binaries, pure symbolic execution found vulnerabilities in 16 programs. Fuzzing found 68 vulnerabilities, and Driller found 77 vulnerabilities. So Driller discovered 9 additional vulnerabilities beyond fuzzing alone, which represents about a 12% improvement. Even more interesting is that some vulnerabilities were discovered only by Driller, meaning neither fuzzing nor symbolic execution alone could find them. This shows that combining the 2 approaches allows the system to reach deeper parts of programs. Driller works well because it balances the strengths of both techniques. Fuzzing performs the majority of path exploration, and then symbolic execution only handles specific input checks that fuzzing cannot solve. The symbolic execution component generates a relatively small number of inputs, but those inputs allow fuzzing to explore many new paths. So a small amount of symbolic reasoning leads to much deeper program exploration. Like any research system, Driller has limitations. First, it is still limited by the performance of constraint solvers. If solving a constraint becomes too complex, Symbolic execution may still struggle. Second, the system depends on the quality of the fuzzing engine. If the fuzzer fails to explore important ideas, explore important areas, symbolic execution may not get triggered. Finally, the version described in the paper focuses mainly on single binaries, not complex distributed systems. So while Driller improves vulnerability discovery, it is not a perfect solution. This slide places Driller in historical context. Early symbolic execution systems like EXE and KLEE focused on symbolic analysis. Later, fuzzing tools like AFL became extremely effective at discovering bugs quickly. Driller represents an important step toward hybrid analysis techniques that combine these approaches. Many later systems like QSYM and Angora build on similar hybrid ideas. So this paper helped influence an entire direction of research. To summarize the main ideas, fuzzing is fast and good at exploring many inputs. Symbolic execution is good at solving complex constraints, but each technique has limitations. Driller combines them in a smart way by using symbolic execution only when fuzzing gets stuck. This allows the system to discover vulnerabilities that neither technique could find alone. The results show that hybrid analysis can significantly improve automated vulnerability discovery. Final question for everyone to think about. Do you think future vulnerability discovery tools will rely on a single technique, or will hybrid approaches like this become the standard? Based on current research, hybrid techniques are becoming increasingly important. Thank you for listening.